Hi everyone, welcome to our new event. Thank you very much for your participation. Today we are here for our new event, QProjects. And during this new series, we will be listening to several research projects by graduate students working in the field of quantum technologies. And by doing so, we hope to disseminate these project topics and increase their impact. Also, we want to listen these projects from the perspectives of grad students rather than the perspectives of the principal investigators. And I think it will be a different experience for all of us. And by the way, I am Onur Pusuluk from Q Turkey. I will moderate the first event of this series with Ecem Duman. Ecem, do you want to say anything before starting?
Well, I guess there is nothing to add, Hocam, and thank you so much for your kind introduction. My name is Ecem Duman. I'm also one of the part of the Q Turkey, and yeah, that's it, I guess.
Okay, and our guest is Lea Gassab today. Lea is currently a graduate student at Koç University, and she is originally from Reunion Island, and she did her bachelor's degree and master's degree at the ENS of Lyon in France. And during her master's, she worked on some quantum biology topics as bird navigation and cognition. And Lea, thank you very much for accepting our invitation. We are patient to listen to your talk. And before starting, let me emphasize that Lea prefers to answer the questions at the end of the talk. So if you have a question, you can wait until the end of the talk, or you can write your questions from chat. Then at the end, we can ask your questions. And Lea, stage is yours. Thank you very much.
Thank you very much, Onur and Ecem, and to Quantum Turkey to invite me today. So first, can you all hear me well? Yes? Okay. So I will share my slide because it's about quantum vision, so you should see something, so it's better. Okay, so now we just ask if you can see my slide.
Yes, we can see that.
Perfect. So I will begin. So today, so first, yes, I'm very thankful to Quantum Turkey to invite me today to be able to talk about my current research and also to present the project we are working at Koç University in the Quest group. And today, so the topic is, can the human eye detect quantum light? So we will see at the end or not if I'm answering the question. And so first, I want to just sorry. So I want to first begin with where I come from, because most of people don't know where is Reunion Island. So Reunion Island is actually a little island here next to Madagascar and South Africa. And so it's quite far from France, but after living here for most of my life, I went to do my study in France. And now I'm very happy to be in Turkey, and I'm doing my PhD in the Quest group, and it's very enjoyable to be in Turkey. I love this country. And I will just show you some picture of my country because also I love Reunion Island. And also it's just not just to show you picture, it's because we are talking about vision, and I want to show you how vision is powerful. Indeed, when you look at this beautiful waterfall, what you can feel is some peace. You have a lot of emotion when you look at some picture. So, for example, if I look now at the participants, I can be stressed because, oh, there is so many people that listen to me. But after I look at this picture and I feel some peace. So, and these are some picture from where I am from. I do some advertising, but I can do also about Turkey because Turkey is beautiful. And also it's just to give you some enjoyable moment for your eyes. And now I'm going to the outline of my talk. So for sure, I will begin with the introduction. After, I will present you quantum biology. So a simple definition for quantum biology and give you some example of quantum biology. Then of quantum vision. So how we are using actually quantum vision in our project. And after this, I will talk about our current project at Quest Group and also our team and present some of our first results. Also, I will talk about some application like medical application, biometric, and finally, I will conclude. So first, let me give an introduction. So to introduce, I think I want to talk about quantum physics because quantum physics is actually like a trend name. Now in the world, many things become quantum. We like the word quantum, for example. I just saw there is a quantum vacuum cleaner. We like to use this word, but actually is when you are studying quantum physics is very large. So you are studying some domain of quantum physics. For example, in quantum physics, a definition of quantum physics that I can give is like it's the study of everything and nothing and the interaction in between. Is some poesy here, but actually I like this because it's also true. You try to study everything, but at the same time, you can go to nothing like the vacuum. And I think in physics, you need to study the interaction. If there is no interaction, the world will not be so interesting to study. But also you have, for example, quantum chemistry, the study of chemical systems when you take the point of view of quantum physics. Quantum biology, we can ask some question, how does the life begin? The life processes such as photosynthesis, and we will see other phenomena of quantum biology. Quantum machine learning, and we can link it, for example, how does the brain learn is a new field. Also, we have quantum optics. So quantum optics is actually the interaction between light and matter. So this is also a very interesting subject. Quantum thermodynamics, and in our Quest group, so we have many people studying actually quantum thermodynamics. So the heat, temperature, environment, and all this. Also, particle physics is very well known and use quantum physics. So interaction between the very small, I think you have heard about Higgs boson or also the CERN in Switzerland is very famous. And just the list is very long, but to finish, we have also quantum communication, teleportation, quantum entanglement that are also some characteristic of quantum physics. So as you can see, quantum physics is very large. So we cannot know everything about quantum physics. So we have to like specialize, I think. For example, me, I go to quantum biology, but every subject of quantum physics is very interesting. And now I want to talk about the difference between classical and quantum, because most of the time we think that they are very different and there is like between them is a big separation. But me, how I like to see it is we are studying actually the same thing. In physics, we are looking at the world around us and we want to study it. So I think to study this world, you can take the classical physics. For example, you put the gloves, the glasses of classical physics and you look at the world, but also you can take another perspective and take the quantum physics. And in quantum physics, there is it's more open because many things can be explained by quantum physics, but not by classical. But many results and all the results from classical physics can be explained by quantum physics. So it's not like they are separate things. It's just we are studying the same thing, but just using different tools. So, for example, I like this picture. They say that this is different thing, but it's just how you see things, and it's about quantum vision. So, to relate to some illusion is quite good. So now let's go to what is actually quantum biology. So I will give a very simple definition. You take quantum physics, you take light. So this is a picture of Sarıyer actually in Istanbul. And you try to take, to study thanks to quantum physics, so the life, for example, bird, you can see bird magnification, but also in water molecule, you can use also quantum physics, and in the air, in the reaction, in the chemical reaction. So you can use actually quantum physics to explain biological system. And we will see what I really mean by this. So actually, quantum physics is about non-trivial quantum effects. So why I insist on non-trivial quantum effects is because you have actually, if you study the particle, you need to use quantum physics. So there is some trivial quantum effects that are in everything. But some non-trivial quantum effects can be, I think you have heard about quantum superposition. So to be simple, quantum superposition. So in classical states, for example, you are inside or you are outside the box. But in quantum superposition, you are both of them. It's like the famous Schrödinger cat. You are at the same time you are dead and alive. Here, the particle at the same time inside and outside the box. So if there is some quantum superposition in biological reaction, this is non-trivial quantum effects. Also quantum coherence. Also to be simple, you can look at it like synchronization, coherence, if you don't know the word coherence. Also, I think quantum entanglement is begin very popular at our time. So what is actually quantum entanglement is even if you have one particle here and you take one other particle very far from this one, even if you want in another universe, you can, if something happened to one, it can, at the same time, it will happen to the other, because actually the two particles cannot be seen separated. They can only be described by, you see, a unique quantum state. You take them together to describe it. You cannot describe this one, and add them. They are just one. Also, quantum tunneling. So what is quantum tunneling is, and this is used in olfaction. So this is quantum olfaction, it is named. To go back, so quantum tunneling, what is it? In classical physics, you see if you have a particle that coming here, if there is a wall here, you cannot go through it, okay? But in quantum physics, this is different, because all is also about probability. the particle actually can go through the wall. There is a probability to have the particle at the other side of the wall. So these are some of the non-trivial quantum effects that we try to find in biological systems in order to explain some biological phenomena that are not well understood yet. And some example of quantum biology is, for example, bird navigation. So it's quite interesting. It seems like bird has like a compass in their eyes, and they can use the magnetic field of the Earth in order to orientate, because you know when they go from one point to another, sometimes it's 10,000 kilometers, they are really precise. And by using this compass, they manage to go from one point A to one point B. This is very well studied in quantum biology. This is the most famous in quantum biology, photosynthesis. So in this case, what really happened is, so when the light go here to the left, so there is like an electron, because thanks to the light, an electron is excited, and the electron must go from one point B to from point A to point B in order to have the reactions that are at the basis of photosynthesis. And the electron just not go like this to A to B, but it takes actually all the different possible paths between A and B. And so it can take the better path because it's doing at the same time, it does all the different paths. So this is how simple definition of photosynthesis. Also, it's quite interesting, we have quantum cognition. So in quantum cognition, we try to explain how our mind is working, because there is many things that we do not understand in cognition, and also consciousness. We try to explain what is consciousness, and also because we don't know really well actually the word consciousness. So we try to use quantum physics in order to make it more understandable. Also olfaction, like I said, that use some quantum tunneling is also a quantum biological subject that's very interesting. And there is also many other different, like DNA in quantum chemistry is very close to, we give it different name, quantum biology, quantum chemistry, but they are very close to each other, all these fields. So. And now I will present you actually quantum vision, but you will see it's not exactly the same that we use in our project, because there is a this quantum vision is more about the biological aspect of it. And you will see in our project what we call quantum vision. So in quantum vision, we have a light, so this is just light. And you know, in vision, so this is our eyes. So in our eyes, we have the retina here at the back of our eyes here. And it goes through some cell. We have some cell just in this retina. And the rod cell and the cone cell. So the rod cell are, the cone cell are responsible as how we can see different color. And rod cell are very effective at low intensity of light. And so the light goes through this rod cell. And here, actually, thanks to the light, there is a reaction that's taking place, is isomerization. And in the isomerization happens in the rhodopsin. So in this cell, there is a rhodopsin. So this is just a molecule. And thanks to the light, what happened actually, this rhodopsin can have two different states. it can go up or it can go down. And so you have two different states. And you can, with this, you can describe it with quantum physics, with a superposition of states between these two states. So this is also a subject of quantum biology. And this is named also quantum vision. But now let's go to the quantum vision I want to talk about for our project. So in our project, actually what we want to do is to use quantum light. And we want to answer some question. One of these questions is it possible to create some quantum state of light that would be more efficiently detected? So can we detect more efficiently if the light is in quantum states? This is one of the questions we are asking. And now if we look at light. So first we have some thermal light. So thermal light is most close to the classical light that we can see around us and is described by classical electromagnetism. So magnetism is all about wave, magnetic wave, electromagnetic, electric wave also. And quantum light, so I put it in comma. So quantum light is just some state of light that are fully quantum. It means that you need quantum physics in order to describe this state of light. For example, we have coherent light. So what is coherent light? So I explain it like a minimum uncertainty state. So what you must know is like in quantum physics, you have the Heisenberg uncertainty principle. So in this principle, to be simple, what it says is like, for example, if you know the position of a particle, you cannot know the velocity, and vice versa. So because you see here actually is the precision which you know, for example, the position and this velocity. And for coherent light, it's just this uncertainty principle is equal to h/2, and the two uncertainty is equal. And for squeeze light is almost the same, but is equal to h/2, but one is smaller than the other one. So what does it give if you, let's go to the visual. So in the visual, for coherent light, you have like a beautiful sphere here, a circle, because the precision for both x2 and x1, if you take these are the same. So it gives you like a circle. But for squeeze light, as I said, it is smaller for one of them and bigger for the other one. So what it gives is actually, you see, this is not a circle, because for circle, you need to have like the same rayon, and here it changed. So this is just, and coherent light is actually laser, you know, like laser. So coherent light is what describes laser light. And also you have Fock states. So what is Fock states? Is in Fock states, I think you have heard about photon. So as you know, in quantum physics, maybe you don't know, we don't care, but in quantum physics, you must describe things by the duality of wave particle. So you have, and for light is the same. So now, because you have this duality wave particle, you have to add the particle, the photon. And in Fock states, you just describe by the number of photons. So you know exactly how many photons there is. So just to to sum up all this, quantum light is just actually, we are taking some different states of light that are described by quantum physics. And also we are asking some questions about this quantum state of light. What are the advantages of quantum state of light over classical light for probing the retina and visual system? So to be simpler, if I send light in some quantum state of light, will it be an advantage in order to know better what is in our eyes? Also, one of the questions, is the human eye capable of detecting quantum light entanglement? If I send you like entangled light in your eyes, can you differentiate it from the light that you are actually seeing? For example, when you are looking at my screen, you are actually using your eyes. So you will see how we will try to answer this in our project. But first, I want to show you, this is a map from our website that one of our members did. And it's a very nice map because you can see how quantum vision is in the world at the moment. So it's a new field, but there is some groups that are studying it, some in USA, in Finland, and in France, but also in Turkey, so in Koç, and also in Bilkent University in Switzerland, and all this. This is a good map. You can look at it in our website if you want later. And I want also to present the team who are working on the quantum vision project at Koç University in the Quest group. So our project leader is Professor Ozgur Ezat-Muteja-Pleoğlu. I'm very thankful to him to be here, to be able to present today also. We have Ali Pedram, who is a graduate student who actually starts the project, and after I join in. And also we have a member, a new graduate student member, Bawan, where we are all working together on this quantum vision project. And we have also collaboration. So we are collaborating with Bilkent University. With them, we want to do some psychophysical experiments. So what, for example, if you send entangled light, what will be the effect on an actual human? So this is an example of some experiments. And also with the University of Crete, who are working on biometrics, you will see on other slides. And we are also open to more collaboration, because more there is collaboration, better it is. So now let's go into our project. So in our project, our objective is to use the tool of quantum information theory and quantum metrology. So quantum metrology is using quantum device in order to measure. The metrology is the measure in order to, and we want to unravel the secrets of visual system, and we want to pave the way for new technologies. And also we would like to help in medical field and also in biometry. So the objective is first the metrology of the retinal network. Indeed, we need to know better how our retinal network is working in order to be able to use it, for example, in devices. Also, quantum biometry and ophthalmology is one of our objectives. And psychophysical experiments, we want, because you know in science that we always need experiment simulation in order to support some of our theory. So this is a very important part. And so I will give you the different steps that we will follow. And you see, I play with your brain a little because I go from down to top. We are so used to go from top to down, but this time I want to go from down to top. So we use an elementary neural network model. So, as you know, our eyes is very complicated. So you don't know if you can imagine all the cells that you have in your eyes and all the rod cells. So it's in million, in milliard. So it's very complicated to do mathematical model, but we have to start somewhere. So the best is to start with a simple model. So we start with, for example, here the rod cell, remember, is the photons that come to your eyes. What you see and what is sending to your brain is because the rod cells are taking it and doing the isomerization. So the light are coming in the rod cell and going to a ganglion cell after that, taking all the information from the rod cell, and they are sending it to the brain. So this is the simplest model. After this, what we would like to do is and we are currently doing this part, is the advantage of untangled photon by proposing. We want to propose some interferometry scheme using both eyes. There is, in the literature, they are using actually the eyes in order to see if one of the papers actually can human detect untangled light. So here in this paper, they are sending some laser light, and thanks to this device here, these two paths are actually entangled. So it's like they are one, something happening here, we have an impact here. And here is a simple detector, and you see we can use our eyes like a detector, because in life, when you are looking around you, you are actually detecting light because the photons are coming to your eye. So you are actually doing like a photoreceptor. But it's more complicated because we see you have your brain that's interpreting the image. So it's more complicated than a simple photodetector. Also, for sure, we will use a machine learning network in order to go to larger scale. So the large scale of the Retina model. For example, here is quite a simple model, but as I said, there is a lot of different cells. So we want to add one layer here, one layer here. And this can be done with machine learning network. But this is at a later stage of our project. And finally, this method, we want to look at so some application to use it for quantum biometry, quantum ophthalmic devices, and also do some, as I said, some experimental proposal with the University of Belgium, Professor Boyager. And so Ali Predem, who is a graduate student and starts in this project, just submitted the first paper for our project. And in this paper, I will present you so what he did. So as I said, this is so our simple model for the retina. But actually, we already so add some layer to it, because here you have the. So yes, so let's look at, this is the real, so the real retina, and this is what we modelize. So here in the retina, you have the cone cell and the rod cell. So this is what detects the light. But after this, it sends the signal to bipolar neurons, we call it neurons, also to retinal ganglion cell. There is some amacrine cells that are more complicated here because, as you can see, they are connecting different cells here. And finally, they are sending it to the brain. So you can imagine how it's complicated to describe this system with a mathematical model. But in our project, what we use is actually, we don't go into describing all. For example, we need to describe every rod cell, every Bipper neuron, to go very in detail in biology. At the opposite, we do a different approach. It's a functional approach. So we are simplifying a lot of our system. For example, here is our rod cell. So here our rod cell. And in the first case, we just send it to a ganglion cell. And then in the brain, what happened, we have some potential action here. But we already add one layer to it, is the bipolar cell here. And the rod cell sent to the bipolar cell and then to the ganglion cell and the same. So this is our first model for the retinal function. And from this, what we do is actually, you see here, we send light. So what we do is we take this model and we put it on some program. We put it on a computer. So for example, here on MATLAB, this is just a name for programming. So, okay. So we send light. And so in our program, so on the computer, we describe the different quantum state of light. So remember what we have: thermal light, Fock state of light, but also we had squeeze light and coherent light. So in our computer, we know the statistical the distribution of these different lights. So we can send it to the rod cell. The rod cells are just modelized by some function. And then we can have a summation. So you can have an idea of how the program is working by looking at this. And this is the results that is in the paper. So if it can seem quite complicated, but actually I will simplify it for you, because you see there is like 3 layers. Yeah, Fock state, coherent state, and thermal state of light. And you see the thermal state is above, after you have the coherent just below, and finally the Fock state here. And if this log area, I think, is not so understandable for you because you did not read the paper, but I can tell you is more the value is, less precise it is. So what does it mean? If you use thermal light, this will be the less precise in order to determine the characteristic of the retina. So here it seems that the Fock state of light, so the Fock state of light was when you describe light by just the number of photons. You can determine how many photons there is. And this Fock state seems to be the most precise in order to probe the human eye. But you have to keep in mind that for sure our model is simple for now. We need also to try to add more layer to it and to see if we still have these results. Because in science, we have two big domains, if I can say, is the experimental one. So in experiment, for example, I send you light in your eyes and I say, yes, I see it. No, I don't see it. This is an experiment. We can do it also on mouse or all this. but here is simulation. So you try to do the model of the retina. So you have to do a simple model of it. And you try to send on your computer, you model the light by some probability, and you send it on your eyes that you are modeled in your computer. And from this, I can go to quantum technologies. So the quantum technologies that can be used is first quantum pupilometry. So pupilometry is a medical diagnostic method measuring the time-dependent pupil radius under light illumination. So by looking at the pupil, actually you can have a lot of information, not just about your eyes, but also about your brain. So this is a method used in the medical field. So for example, if you use quantum light, maybe you can have better diagnosis, because we just saw that by in our results, if you use quantum state of light, you might have better precision. But also one of the applications is quantum biometrics. So in quantum biometrics, you need to identify people through some unique characteristics. For example, everyone knows a fingerprint. So this is a security system used. And what this actually is well done. You can look at this website by Professor Kominis at the University of Crete. So he's working on this subject. And what he tried to do is actually to do a system, a security system, using not the fingerprint, but a fingerprint that you have in the eyes. So how you want to do this is, for example, if I send you, here you can see in the eyes, I send you a square like this of 25 pixels of light directly in your eyes, everyone will see it directly. But if I decrease the intensity of light, actually you will not see the pattern like this, but everyone will see different pattern. Why? Because this is like a fingerprint, how the loss in your retina and also the interpretation in your brain and all this work like a fingerprint. So it's trying, and this could be more secure than, like, for example, fingerprint, because if it uses quantum physics, you know, in quantum physics, if I think, for example, in cryptography, if you use quantum physics, for example, if I have a message I send to someone else in another place, but the information share is quantum. If someone come and in between, they will like have a direct impact in the quantum state. And this is not true in classical physics. So this is why if you use quantum physics, this can be more secure. And also, yes, why I wanted also to emphasize that quantum pupilometry can also be used for diagnostic of different disease in our brain, like Alzheimer. Notice that many diseases are not well understood. So maybe with this we can so have some positive impact in the medical field. And finally, I want to conclude. So because the subject is quantum vision, I just conclude with some image. And yes, because, so what I've told you during this presentation is I present you general quantum physics and quantum biology, and I present you our project, but also I forget to mention about an important part of our project is to link it to the brain, because everything that we are seeing is actually directly linked to our brain. As I said, all the signals that are coming to your eyes are going after to your brain, and the brain is interpreting the image. You can see here is interpreting the three. And so the brain is an important characteristic here. And also, yes, there is some questions that can emerge, because you see, we are looking actually at a quantum world, because many things are described by quantum physics, but we see it classically. So this eyes is very not well understood how we are seeing image, but every day and at every moment you are seeing things, and there is a direct impact in our lives. So I think it's quite important to better understand how eyes is working. And just to finish, because yesterday I went to by chance I went to the Museum of Illusion in Istanbul. I found this very nice to conclude with this, because for example, here I can assure you, like, these two lines are the same length, exactly the same length. So I was quite surprised, and this really bother me at the museum. And here, if you don't stare it too much, because it can give you some brain headache, because you don't, it's very hard to look at this image. You can see like a quantum superposition if you want. And if you do this little game in Turkish and English, you can see like how your brain can trick you. So this is just to show you how eyes can trick us, and how what we are looking around, we can all see it differently, I think. So with this, I think I am finished, and this is bibliography. Also, I want to thank you in every language. And if you want to contact me or learn about our press group, you can visit the website. So now I'm open to any question. I will be happy to answer.
Thank you very much for this great talk, Lea. And now I'm enabling wait to unmute option. If you have any question, you can unmute yourself and ask your question. Also, you can write your questions to the chat. I think there is a question from chat from Can Yilmaz. He asked that, can we detect psychological disease such as bipolar and schizophrenia in quantum pupilometry?
They are actually working on it, but this is not still like, I cannot say yes, this, because quantum pupilometry is like very new. They are just begin to work on it, and for now is like what they want to achieve, but for now it is not true.
But I think this is one of the long-term objectives of your project.
Yes, because yes, in Crete we are working in collaboration with Professor Kominis, and he's directly working on this. And with our research, we want to add to his project. So yes, this is one of our aims. No problem. Thank you for your question.
Okay, I guess I can ask another question. It will be from the Google form, actually. Actually, you mentioned about the simulation model that you use, Lea, and as far as I remember, you mentioned that it was like very simple, not too complicated. This is like, I guess, the biggest advantage of the model you use. But you also show that there are also few research groups that work in the same field in quantum fusion. So I want to ask you that what is the main difference between those, the models that the other research groups and yours? Like, what is the main difference? Is it just a much more simpler version of them, or yeah?
No, it's just we are not working exactly on the same thing. Our characteristic is we're trying to be the first to try to look at how different quantum state of light can probe the human eyes. Mm-hmm. So I think on this we are the first one to work on it, but many of the other group are working is very near our project, but they take some different, you see, they go to a different angle. For example, in Switzerland, they are more, they are trying to look at if our eyes can detect actually 2 photons at the same time. It's more complicated, but you see, it's different angle.
Yeah, I guess it depends. So it depends on the purpose of the project as well. Yeah. Okay.
And I think there are some other questions from chat. Let me read one of them for you, Lea, from Ravand Abdullah. He thanks very much for the talk, and then he says that it was very fascinating, it was brilliant, and I'm a physicist. Most of your talks were new for me. Could you please link your scientific view of eyes to déjà vu?
So this is a good question. So I think it's also a complicated question, because déjà vu, I think, is something linked more to our brain. So everything linked to our brain is very complicated for now. So I don't know how to link it, for example, with my talk, to be honest. But maybe quantum physics will be able one day to answer this question. But many of how our brain is working and our mind is working is very not well understood by the scientific community yet. But we are trying to go over it, and there is like quantum cognition that try also to work on it. So, but I don't have direct answer for this.
Lea, let me add something to this question. I think we can consider the possibility for déjà vu as an illusion, and I think you see some connection between illusions and quantums of the vision. Am I right?
Oh yes, you see, like you want to link déjà vu to illusion. Mm-hmm. Some illusion. Or also, I think a déjà vu can also be because in your brain you have some memory, you have seen something, and can also, when you look at you are living another experience that are linked to a past experience. So maybe this is also something with a memory that you think you did not have, but you have. I don't know if it's illusion, memory, or all this, but maybe it's an illusion.
Okay, great. So there's another question, actually, one of them from the Google form and also chat box. I think I can combine both questions. First part will be, I guess, you also mentioned that one of the application of the quantum vision is machine learning, right? And but I think it would be really much more great if you can give us much more detail about like how they intersect, how quantum vision and machine learning can intersect. And related to this actually, there's a also question from asked to you on the box, that how far in the horizon are we going to realize quantum biology type applications, like in 3 to 5 years or 5 to 7 years?
So about quantum, so machine learning, we will use it because you see, if it's like in, I don't know if in deep learning we are using like neural, sorry, I go back. So let me show you my, I think this will be easier. So so for now we are not at this stage, but what we want to do is, you see here, it's quite simple. You have like one layer, but if you want to add more layer, it will be more complicated. But by using machine learning, so machine learning here, for example, is like a little image that can symbolize it. So each of the nodes here are neurons, and they are linked into all the neurons. So actually your retina can be seen also as like, for example, each node here is, you can have the rod cell, and after you can have the bipolar cell if you simplify it. So it is how we can like create a more complicated system, going to our little retinal model to bigger model by using this machine learning method. And how we can train it is, you see, in some literature, we have well-known experiments that can look at how the threshold of our vision, for example, 7 photons, if I remember well. And thanks to some probabilistic curve, we can like try to train our machine learning model, and with actually to train our eyes. But because you see the border between eyes and brain is like, is like we can look at the eyes maybe like a continuation of our brain. So, but for now, we don't know exactly, like we did not first begin so this quantum machine formalism, but it's what of our thought about it. But maybe in the future, I will be able to answer you better on this.
Yeah, thank you.
I think there's a related question, one more related question from chat, from Pupilometry. Let me read once again. When your team built the neural network, did it use a quantum machine learning package, such as TensorFlow Quantum or classical neural networks? I ask this because I wonder how your team regards sense as a measurement apparatus. Shortly, does this model fit one-by-one measurement scheme? And Shamim asked the same question I ask, I think, demiş Pupilometry.
So, no, we are not using quantum machine learning package like TensorFlow Quantum. And as I said, for now, we did not go into machine learning yet. We are like, at the moment, we are building like some interferometric setup. So this will come at the later stage, at the end of our project. But in our program that we are currently doing, we are not using a quantum machine learning package like TensorFlow Quantum. And what? So yes, I don't. Is there any other question related to this that I did not answer?
I think in the second part, he wrote that, I asked this because I wonder how your team regards cells as a measurement apparatus. Shortly, does this model fit von Neumann measurement scheme? Do you think, I think the rod cells here can be regarded as measurement apparatus to detect the light?
Yes, here the rod cells because they are like the first, they are the one who are collecting the light and doing the isomerization. So yes, the rod cell are like measurement device here. And after you see the rod cell, here you have some W1, W2, and W3. So this is are the characteristic, if you want, of your rod cell. And from this, the rod cell will send, for example, a message to the ganglion cell. So that will send different message according to the weight here, the W. And what we actually try to do and what Ali did in his first paper for a project is actually try to describe, to know this W by using some methodologic method like quantum Fisher, with a Fisher information measurement and Kramer lower bound for those who are more in this, know more about these methods. But yes, if maybe I went too far, but yes, the measurement apparatus are the rod cells.
But as far as I understood, you do not consider the specific photoisomerization process. Instead of this, you are using the statistics of these different classical and quantum states. I think we can interpret this in this way. Probably your measurement apparatus rod cells fit von Neumann measurement scheme in this way because you use the statistics. It means that the states are collapsed before sending information to the brain.
Yes, exactly. Yes, that's a good point that you made because here what we consider as quantum is just the light. So the isomerization process here are not described by quantum physics. Okay, so here we have some probability according to the state of light. So if it's a fog state of light, if it's squeeze light or current light, we will have different probability, so statistical, statistical distribution. And this will go to the rod cell and after the ganglion cell. But we do not describe the isomerization as a quantum biological.
I guess we don't have any more questions left on the chat box.
There is one more, but I think Ecem, there is a related question from the form. Maybe you can ask this.
From the form, right? Okay. Which one I couldn't understand which one you're talking about, Ecem, but I can ask one question from the form as well. There is this question, if available, would you mention the proposed quantum vision algorithm's complexity-wise difference with its classical alternatives in terms of peak O notation?
Well, so as I said, we don't choose quantum. We don't choose quantum programmation. We just choose classical. So we did not we did not have comparison because we just choose classical programmation. So there is nothing I can say more for this question. But if we do yes, a comparison, but for now we don't choose a quantum. the contemporary.
Let me ask this question, Ecem. It was, what can be said about the existence of quantum light in the tapetum lucidum layer in the eyes of animals? And for the others, let me read some sentences from Wikipedia about tapetum lucidum. It is a layer of tissue in the eye of many vertebrates, laying immediately behind the retina. It is a retroreflector, and it reflects visible light back through retina.
Okay, so for sure, because as you saw here, we don't go into too much detail because it will be very complicated to be able to model, for example, every cell. So to go now to the specific layer is for sure we did not investigate it, but there is so many questions like this that are very interesting, and I think the person who asked this question should study this, and and this is very interesting.
Well, I think we can continue with much more personal questions maybe. And I also wonder the answer of this question as well, to be honest. What's motivated you to select this topic for research? It's very few people works in this field as you showed. And also I want to ask you that question as well, like how does it affect, there are few groups works in this field, so yeah.
So, me actually, when I was doing my master, I went to South Africa and I did an internship in quantum biology. And from this, I started to be very interested in quantum biology. So I knew that I wanted to direct my topic in quantum biology and more in actually quantum cognition, to be honest. And after, it's more how I end up here doing in this project is more about how is life. I asked some group in order to do my PhD, and I found Turkey and Istanbul at Koç. And I was very interested in the quantum vision projects. So it's like by chance, I found it. And it's also because I was looking for quantum biology subjects.
That's good, I guess.
And there is a question from chat that we forgot. It was a technical question. Let me read once again. I think to detect squeezed or entangled light by eye, we can work by two levels. First, we can filter the light. Secondly, we can attach filter or attach detector at rod or cone cell. Which approach you are following? Is it possible to follow both procedures?
So actually, I think I am on the good slide to answer this question. So for example, here, how in this paper, actually, they try to answer the question if we can detect entangled light with the eye. And you see what they do is actually they send, this is here, entangled light to a photodetector and to the eye. And here, the human who is here are responding to some question like, do you see or do you not see the photon coming? Or do you see light or do you not see light? And from this, you can get some probability if he see or he don't see the light. And here, with the photodetector, you can get also some probability. And actually, this probability that you can get after this, according to the value of the probability, it's more complicated than this, but you can, like they call it a quantum entanglement witness. They can develop mathematical tool that tell you if it's yes or not entangled. So you see, it's not like I receive some light. Oh yes, it is entangled. No, it is not. Here, it's from the probability after it's very long mathematical development that you need to do. but you can get the information if the light was or not entangled. And here they don't choose actually, what they use is they add some, it's called like operator, displacement operator, in order to they amplify the signal. Because what is very hard is when you have entangled light is to preserve this entanglement, so to not affect it. So what we will work on also in our project is, for example, to try to look at the two eyes, if we send to two eyes and not to a detector. And also here it's some laser light, but we want to, if we can try some, for example, here to add some squeeze parameter.
Okay, thank you so much, Lea. If our guest doesn't have any questions, I don't know, I can see, I guess I didn't miss anyone, any question? Onur Hocam, do you have any questions or anything to add?
Let me double check the questions from form, not to forget any of them. And actually, there's a question. It asks that, can we use quantum pupilometry and biometrics to use encryption on our sensitive data on our phones and tablets?
So they want to use like quantum quantum pupilometry for some is really for a secure system, so like for fingerprint. So to use it on, maybe one day, for example, some of the phone use a fingerprint to open. Maybe they will one day use quantum pupilometry to enter your phone. I don't know, but maybe.
I have a theoretical question rather than an application question. As you mentioned, you consider the retinal network, and you don't focus on the photoisomerization step here. But in literature, in quantum biology literature, there are a lot of papers that investigates this photoisomerization process from the perspective of quantum information theory. Are you planning to do some related works also in this project?
Yes, actually, we talked a lot of about this part with Ali, and I think in a later stage, what we want to add is also this isomerization, like you said. But for now, we will not do it, but for sure we are considering it.
Thanks, Lea. And Ecem, did you forget anything?
Let me see. Okay, maybe we can ask one question actually as the last question. Can you talk about the research opportunities in your research group and also your institution? I think our audience can also get some information about that.
So you mean to join the Quest group?
Working as a grad student, or any other stuff, any research opportunities, or how they can collaborate.
So for sure, yes. I know like my supervisor, Professor, and everyone in the team are very happy when we receive some email of graduate student or even undergraduate students who want to work with us. For example, in our group, there is a lot of undergraduates that come and because they are very interested in this subject, they come and we can give them something to collaborate. And so we are always open to collaboration. And I think the best way to be able to enter the group is just to don't be shy to send email, because we are not scary people. We like to, more we interact with other, more better it is. So yes, don't be shy. Just
yeah, sending email is free, totally free. So you can send and ask them any questions on your mind. Yes, I guess that's it. Onur Hocam.
I think we finished all the questions. Let me stop recording.